A huge concept when it comes to designing an OSPF network is how are you going to have your area or your areas laid out? What is an area, first of all? Well, an area is a collection of links, of networks in other words, that are running OSPF. And it's important to understand that a router might have multiple interfaces. It's not the entire router necessarily that belongs to an area, it's the individual interfaces on the router. In fact, I could have a router with different interfaces that belong to different areas. At a very basic level, we're going to have just a single area, a backbone area. And we could certainly have additional areas, and we'll talk about that. But let's just start really simple and imagine that we've got these three network links illustrated on screen, and they all belong to the same area. Notice that routers R1, R2, R3, they have interfaces that belong to this area. Let's call it area 0. And as a result, the map that they construct, running the Dijkstra shortest path first algorithm, the map they construct, their view of the topology should be identical. They should see area 0 the same. And again, this is done by doing a calculation. They each do their own calculation and they should come up with the same result. They should have the same view of the topology. However, some networks, some larger networks, take all of their links and their routers and they carve the network up into different areas. Here we have area 0 in the middle, area 1 on the left, and area 2 on the right. And within each of these areas, we're running that Dijkstra algorithm. In fact, that's one of the big reasons that has traditionally been given for breaking a network up into different areas. If you have a really, really large network, it takes some extra processing time on the part of the router to do that Dijkstra algorithm calculation. And we'll talk about whether or not that's a relevant reason to do it today or not in an upcoming video, but understand that each area is independently running the Dijkstra algorithm, and we're generating a database for each of these areas. And specifically, I want you to notice routers R3 and R7. Notice that on router R3, two of its interfaces live in area 1. One of its interfaces, the interface going down to R4, it lives in area 0. That's the point that we were making a moment ago, that different interfaces can live in different areas. If we have a router that has interfaces in different areas, then that router, R3 and R7 are examples in our case, these routers are called ABRs, area border routers. Router R3 not only has a database, it not only runs the Dijkstra algorithm for area 1, but it has a database of view of the topology. It runs the Dijkstra algorithm for area 0 as well. Router R7, it's got a database for area 0, it's got another database for area 2. It sits at the boundary of these two areas. And we could do some fancy things as we're going from one area to another area. We could summarize networks. But at this point, I just want you to understand that within each area, we're running the Dijkstra algorithm. If we have more than one area, our backbone area that we spoke of, it has to be area 0, or some people use a dotted decimal representation and they say it's area 0.0.0.0. And there's a rule that says all of the other areas, area 1, area 2 in our case, all of the other areas, they need to be adjacent to area 0, to the backbone area. And in this case they are. Area 1 is adjacent to area 0 because R3 has interfaces in each area. Area 2 is adjacent to area 0 because router R7 has interfaces in each area. But let's say that we had, I don't know, maybe a merger of a company. For some reason, we had our areas like this, where area 0 is at the left, area 1 is in the middle, and area 2 is on the right. Area 2 does not appear to be adjacent to area 0, does it? Will this work? No, this will not work in its current state because area 2 is not adjacent to area 0. But there is a workaround. There's a fix for this. And this fix is called a virtual link. We can specify that we're going to transit area 1 to get back to the backbone area, to get back to area 0. What we will do, we will go into R3, we will go into R7, and we will define this virtual link. And logically, we can make it look like, over this virtual link, that area 2 really is adjacent to area 0. And these topics that we're talking about right now, of having multiple areas, of configuring a virtual link, we're going to save that for our IC&D 2 discussions. Right now, for the IC&D 1 level, we're going to focus on just a single area. When one of our router interfaces is configured for OSPF, it's going to have a specific OSPF network type. Let's talk about some of these common OSPF network types. First is a broadcast network type. We've seen this before. This is where we have a subnet on a broadcast medium, some flavor of Ethernet perhaps, and we've got all these routers connected to the same subnet. Maybe they're connected into a Cisco Catalyst switch as we see here. And these routers, they need to talk to one another, but if we were to form a full mesh of adjacencies, we saw earlier that this did not scale very well. Do you remember the solution? The solution was to designate a single router that would form adjacencies with all of the other routers. That way they didn't have to form adjacencies with each other. And that router was called a DR, a designated router. We also had a backup designated router in case the designated router became unavailable. So we are electing a DR and a BDR with a broadcast network. The hello interval for a broadcast network is 10 seconds. Every 10 seconds, we're going to be sending out a hello message. And if our neighbor has not heard from us within what is called the dead interval, which is 4 times the hello interval, 40 seconds in this case, our neighbor is going to assume that we're not up any longer. And because this is a broadcast network, we're dynamically discovering our neighbors. There's no need to go in and use the neighbor command to statically say, here's the IP address of a neighbor. That's the broadcast OSPF network type. Next is the point-to-point OSPF network type. Here we might have a couple of routers at different sites interconnected over an IP WAN. Maybe the protocol on the WAN is the point-to-point protocol. Maybe it's HDLC. Maybe it's frame relay. But notice that there are only 2 routers on this network segment. Since there are only 2 routers, we don't have a scalability issue where we might have to form too many adjacencies like we did with the broadcast network type. So there's no need to elect a designated router or a backup designated router. The hello interval is still 10 seconds here, and therefore the dead interval is 4 times that, it's 40 seconds. And there's no need to use the neighbor command because we can discover who is at the other end of this link. There's only one other router. That's the point-to-point OSPF network type. Next is the non-broadcast OSPF network type, sometimes referred to as a non-broadcast multi-access network, or NBMA. This might be a frame relay network. Let's pretend that router R1 is at our headquarters, and routers R2, R3, R4, they are all at different remote sites. And maybe they all belong to the same subnet. It would be a good idea to have a designated router here, so we do want to elect a designated router. But the challenge is, this is a non-broadcast medium. And since we don't support broadcasts or multicasts over this non-broadcast medium, this means that we're not going to be able to dynamically discover our neighbors. We're going to have to go in and statically configure the IP address of a neighbor. And if we're going to have a designated router for all of these routers that we're saying belong to the same subnet, we need to pick a router strategically that is adjacent to every other router. In this case, that's going to be R1. R1 is the only router that has a connection going out to R2 and R3 and R4. And even though in some topologies we might have a backup designated router where we have another router that connects to all other routers, in this case we do not. In this case we will have no backup designated router. And one of the challenges we might have here is, how do we make sure that R2 and R3 and R4, how do we make sure that they do not become the designated router? To prevent them from being elected the designated router, what we can do is set their OSPF priority value to a 0. And we have R1's OSPF priority value set to something higher than 0. That's going to force R1 to become the DR. And do you see why it needs to become the DR? It needs to be able to form an adjacency with all of these other routers. And it's the only router in the topology that has a layer 2 connection to each of the other routers. With the non-broadcast OSPF network type, the hello interval is a bit longer. It's 30 seconds, and therefore the dead interval is 4 times that. It's 2 minutes. It's 120 seconds. And in this non-broadcast network, we're not going to be able to dynamically discover all of our neighbors. So we will need to go in and give a neighbor command to statically configure each of our neighbors. And finally, we have the point-to-multipoint OSPF network type. Topologically, it looks about like the non-broadcast OSPF network type. What's the difference? Well, if we configure our interface that's running OSPF, if we configure it for point-to-multipoint, what it does, it treats each of these permanent virtual circuits, like that dashed blue line from R1 to R2, and the line from R1 to R3 and R1 to R4, each of those permanent virtual circuits, each of those logical paths, are going to be treated as a separate point-to-point connection. And we said that a point-to-point connection did not need a designated router or a backup designated router. Same thing here, because this appears logically to be three separate point-to-point connections. There's no need for a DR or a BDR. The hello interval for point-to-multipoint is 30 seconds, therefore the dead interval is 120 seconds. And because a point-to-point network does not need a neighbor command to discover the router at the other end of this link, same thing here. This logically represents three separate point-to-point connections, and there would be no need for the neighbor command. Each of those three individual connections, acting as separate point-to-point connections, could simply have the routers at each end discover one another. And to sum up this information as sort of a reference for you, here's a table that shows us these four different network types, whether or not we're going to be electing a DR and a BDR for these network types, what the default hello interval is, and remember the dead interval is 4 times the hello interval, and we also are saying whether or not we're using the neighbor command. Let's talk about some defaults though. If I have an Ethernet network, what is going to be my default OSPF network type on that Ethernet interface if I don't go in and change it, which I could. I could go in and administratively say, this is your OSPF network type. But if I don't do that, the broadcast network type is going to be used on an Ethernet network. The point-to-point network type, that's going to be used by default on frame relay point-to-point subinterfaces. We haven't talked about frame relay yet. That's coming up later. And the non-broadcast OSPF network type, that's going to be the default network type on frame relay physical interfaces and multi-point subinterfaces.